Hello there. So let's go ahead and then cover today's material. Today we're going to talk about temperature and heat. So what is temperature? What is heat? How those things affect matter? Then we're going to see those topics um, in the coming slides. The first thing is like temperature and its measurements. So every physical quantity needs a way to measure, and like of course you need to have a certain kind of way of measuring it, and it has its own unit and so on and so forth. So what are the difference between temperature and heat? Heat is mostly it's energy, an internal energy, and that results in change in temperature, whereas temperature is just like a mere measurement of like how warm or how cold a certain environment is. So how do we measure temperature? Temperature is measured using thermometers. So most of the time we use a special kind of liquid, such as mercury, in the thermometer, inside the thermometer, that usually expands with temperature increment, and it contracts with temperature decrement. Okay, so for instance, like as you can see here, we use thermometers to measure temperature at 0 degrees Celsius. You can see that like the thermometer liquid level is up to here, but if you put it like in a boiling water at 100 degrees Celsius, then that liquid expands, and then it increases in level, and then it reaches to 100 degrees Celsius mark. So in general, there are three distinct temperature measuring scales. The first one is the Celsius scale. So in the Celsius scale, the freezing point of water is 0 degrees centigrade. Ice and water coexist at that temperature, whereas the boiling temperature, the water steam mixture, is at 100 degrees Celsius. Okay, so between the distance between those two values, between the freezing and the boiling point of water, there are 100 equal segments of degrees. The other one is the Kelvin scale. The Kelvin scale it's the SI unit of temperature, and in a Kelvin scale we just simply call it like Kelvin without using the term degree. We say 25 degree Fahrenheit, 25 degrees Celsius, but when it comes to Kelvin, we just simply say 25 Kelvin. So then the Kelvin scale is something like that we widely used in the scientific community. Then for instance, like there is something we call it the absolute zero. The absolute zero means 0 Kelvin. So the 0 Kelvin is like it has its own kind of scientific interpretation with it. So for instance, in a certain ideal gas means like as temperature increases, then pressure increases. Okay, as temperature decreases, then pressure decreases, just in a linear fashion. So for instance, if you consider like three different gases, we're calling them trial 1, trial 2, trial 3. What happens as the temperature increases? Their pressure increases. You see here's the temperature. As the temperature increases, then the pressure increases. As the temperature decreases, then the pressure also decreases. What happens is at a certain point, for instance, if you keep on reducing the temperature to 100 degrees Celsius, to 200 degrees Celsius, what would happen is like the pressure inside a container of the ideal gas. So for instance, let's say you have an ideal gas that is packed in a container. Okay, so when you warm this thing, what would happen is like the 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 atoms or the molecules of this ideal gas, they will start to move faster, and then they are going to create, they try to expand, and because of that, like they try to create some kind of pressure on it. I mean, the pressure will increase. But as you decrease the temperature, what will happen is like the motion of those molecules will reduce, and then as a result, like if you keep on reducing the temperature, you'll reach to a level where those molecules are no longer exerting any kind of pressure on the container. That means like pretty much they become, you know, inactive, let's put it that way. So that temperature is what we call it the absolute zero, and that temperature happens pretty much for every ideal gas. So if you have another ideal gas, and then if you let its temperature to drop to an absolute zero, then at that absolute zero, what you will end up with like with a pressure of zero value. Okay, so then that value is 0 Kelvin. So absolute zero is at 0 Kelvin. Then that 0 Kelvin is found to be negative 273.15 degrees Celsius. Okay. The other temperature scale is the Fahrenheit scale. This is the most commonly used one in the United States. So the freezing point in the Fahrenheit scale is 32 degree Fahrenheit, and the boiling temperature of water in a Kelvin scale is 212 degree Fahrenheit. And there are 100 equal divisions between those two values. Okay, so now just to summarize, the ice point for on a Celsius scale is 0, on a Fahrenheit scale it is 32, on a Kelvin scale it is 273. The steam or boiling point for water on a Celsius scale it's on 100, on a Fahrenheit scale it's 212, and on a Kelvin scale it is 373.15. Okay, so in general there are ways like to convert from one temperature scale to another temperature scale. So the very first one is a temperature scale that we will use like to convert this to this. This one is temperature in Kelvin, and this one is temperature in degrees Celsius. Okay. So to convert Tc to Tf, you will want to use this equation, 9/5 Tc plus 32. Whereas to convert Tf to Tc, you will be using 5/9 into parenthesis Tf minus 32. So those temperature scale conversions may seem a little confusing because there's a lot of similarity between those two. You know, you see 9, you see 5, you see 32, and so on and so forth. But there are two distinct things that you need to remember. One is like there is a plus sign here, whereas there is a minus sign here. Number two, what you need to remember is like the most common mistake that students make when they are converting one unit to another unit is like the lack of parentheses or putting a parenthesis on the wrong spot. So, you know, sometimes I see students putting parentheses here. No, that parenthesis is not there. Okay. And I see that like some students like ignore this parenthesis, but this parenthesis is there. Okay. So always like keep in mind which equation you are going to use. We're going to demonstrate this like using, of course, we are going to use examples, and we will do some examples here. Okay. So keep in mind the signs, plus minuses, and the presence of the parentheses, and of course one is 9/5, the other one is 5/9. Okay. Then the other item is like the distinction between temperature and heat. Heat, as we mentioned it, is the energy that flows from one object to another object. Okay, because of temperature differences. It's energy in general. Like you can say that like heat is energy. Okay, so it's represented by uppercase Q. Since it's energy, its SI unit is, of course, it's joule, and it is uppercase J. Okay, so in general, like you know, like for instance, you have water. and then you warm it up and you change its temperature from certain level to another level, right? So how do you find the amount of heat energy required? So how do you find it? Normally there is an equation, we call it Q is equivalent to the mass of the water that you have multiplied by its specific heat multiplied by the change in temperature. So in this equation, Q is heat and mostly measured either in joule, but in this material we will use calories a lot more. Okay, and then M is mass and C is specific heat. Okay, and then delta T is change in temperature. Change in temperature means final minus initial. Change. Okay, so this is the amount of heat that you will need, to warm certain object, like from a certain temperature to a certain final temperature. Okay, and this specific heat, mostly it is measured in calorie per gram per degree centigrade. This is the amount of heat energy that you need to raise a gram of a certain object by 1 degree centigrade. Okay, so as an example, like C for water, C for water is 1. What does it mean? It means like to raise the temperature of 1 gram of water by 1 degree Celsius. How much heat energy do you need? You need 1 calorie. Okay. So the other thing is that you need to keep in mind is like there is another kind of heat known as latent heat. Latent heat. This is the heat that you need for phase change. Okay. This is like a heat that you need for phase change. Like for instance, there are two types of latent heat mostly we will commonly encounter, especially for water. So one is heat of fusion. Okay, and you can calculate heat of fusion as LF, which is a constant, multiplied by mass. I'll come in a moment, like why do we use that one. And the other one is known as like Q for vaporization. It means that's calculated as LV multiplied by M. Why do we need this one? The latent heat of fusion is the amount of heat energy that you need to convert, ice at what temperature? At 0 degrees Celsius to water at 0 degrees Celsius. You see? You cannot really reach from solid ice to steam right away. What do you need is like in between there are phase changes that happen. A phase change is like from a phase of solid to a phase of liquid, and then from a phase of liquid to a phase of what do you call gas, right? So over here it's like, when do we use this equation? Whenever we have like water at what temperature? At 100 degrees Celsius. That means literally boiling water to steam. at 100 degrees Celsius. Okay, so to find that, what you need is like you just multiply LV, which is a coefficient of the latent heat of vaporization, and that value is 540 calorie per gram. You need 500 calories of energy to convert 1 gram of water to 1 gram of steam, whereas LF is equal to 80. It has a similar definition as LV. When do we use it? When you are converting or calculating the amount of heat required to melt ice, literally, just without increasing its temperature. All right, because we cannot use this heat equation for phase change. Why? Because there is no any change in temperature, because delta T here is 0. When every time you are using this equation, the change in temperature is 0. I mean, there's no change in temperature. What happens is like that latent heat, as the name implies, latent means like something that is hidden, something that's sleepy, that you don't know is there, but of course it is normally there. Okay, so pretty much like, you know, try to remember those items. We're going to reinforce this all knowledge like by doing some good examples. Okay, then of course there's temperature. We already talked about temperature. The temperature is like quantity that indicates whether or not and in which direction heat flows. Okay, so always heat flows from a higher gradient to a lower gradient. That means like if you have two objects next to each other, right, A and B, if A is 100 degrees Celsius and BB is at 50 degrees Celsius, what will happen is like heat will not flow from B to A. Heat will flow from A to B until both of them reach to a common temperature. Maybe, I don't know, 75 Celsius and 75 degrees Celsius. Okay, something like that. All right. Then the last item that we will be discussing here before we proceed and start calculating, you know, a few examples, the flow of heat. In general, there are three different ways where you have heat flow. The first one is by conduction. By conduction means like you have two objects just in contact to each other. So let's say you are here and another object is here. So as in the previous example, if this is at 100 degrees centigrade and this is like at 50 degrees centigrade, then heat flows from A to B until they both achieve a common temperature. Common temperature of, I don't know, you can call it 75 or something. But anyway, there is a direct contact between object A and object B. That kind of heat transfer is known as by conduction. Heat by convection, it's like your AC system. Like, you know, you have a house or you're in your apartment and there's a heater here, right? Then the heater is going to get heated up, right? Then what will happen is like all part of the house will be warmed up by, you know, by the air mass that is flowing around in the house, right? So therefore, this is the type of heat that you see by convection. As the name implies, it's like heat a volume of air, then move the air by blower or natural flow. You just follow the natural flow of air, and then, you know, it warms like every part of your house. Okay. The other one is heat transfer by radiation. That is like, you know, if you are in your car and, you know, in the summertime, probably early in the morning, temperature outside might be really fair, but if the sun is shining through the window of your car, right? So what happens? What would happen is like the light rays will go in. That means the heat being transferred in the form of electromagnetic wave, and then they will warm up the chair, they will warm up other parts of the car, and this whole room is going to be really hotter than the outside. Why? Because some of the radiation energy went into the car, and then it was unable to escape back into the environment. But in general, like that is like the heat transfer by electromagnetic wave. It shouldn't be, I mean, this is like just to explain it in terms of a little bit exaggeration. Of course, it's also like heat from sunlight. The heat normally comes to us in the form of electromagnetic wave, right? So you just feel warm when you're outside in the sun, because heat is being transported in the form of radiation. Okay, so that's pretty much it, like about the theory. Then let's go ahead and then probably start solving a few examples. So the first problem that we are interested in is like, there's a direct example from your textbook and would like to revisit it. It is fully solved, but I like that example, then I'm really trying to redo it again. So problem is example chapter 10.1. So the problem states the following: if the specific heat of ice, so let's list what our given parameters are. So C for ice, 0.5 calorie per gram per degree Celsius, right? Then states how much heat would have to be added to 200 gram of ice. So the mass is given initially, so temperature initially is given, which is negative 10 degrees Celsius, to raise the ice to the melting point. So question A is, how much Q do you need if the final temperature is melting point? Melting point means 0 degrees Celsius. Okay, so the solution for this, you're going to go ahead and then apply the heat equation, mc delta T, right? So your Q is going to be equal to, the mass is 200 gram, C is 0.5 calorie per gram degree Celsius, and then the change in temperature is going to be T final, which is 0, minus T initial, negative 10 degrees Celsius, right? Then this degree Celsius cancels with this degree Celsius, gram by gram. Okay, the only thing left is of course calorie. Then your Q, if you multiply this everything, 0 minus of minus 10 is going to be 10, right? Anyway, so that means 200 times 0.5 times 10 calories. So this is going to give 1000 calories. All right, then the problem has part B. Part B states like, completely melt the ice. So how much heat energy do you need to completely melt the ice? That means like you are asked to find Q melt, or sometimes known as Q fusion, to melt it. So if you remember, like in the slide I tried to mention what is Q fusion. That means the melting. L fusion multiplied by M, where L fusion is a constant, and it's known as latent heat of fusion. Okay. And L fusion is 80 calories per gram. So you need 80 calories for every cube of ice to convert it from ice to water. So the result, like your Q fusion, you can call it Q fusion or Q melt. It is, both are the same thing. L fusion is 80 calorie per gram multiplied by the mass. So the mass is 80, rather 200, right? So ground cancels out. Then your Q fusion will be 16,000 calories. Okay. Then the next problem that I'd like to look at is like E1 in your textbook. At the end of the chapter, there are exercise problems that we normally solve. So E1 states an object has a temperature of 22 degrees Celsius. So it's given. Its temperature in Celsius is given. Okay. Then question A is, what is its temperature in degree Fahrenheit? So A is its temperature in Fahrenheit equals what? So the solution is like you just go ahead and then simply apply the conversion equation. For TF, the equation is what? 9 over 5 TC plus 32 without the parentheses. All right. So TF equals 9 over 5 times 22 plus 32. If you plug in those things like in your calculator, you're going to get 71.6 degree Fahrenheit. Okay. B, it's saying what is this temperature on the absolute Kelvin scale? It means in Kelvin. To convert Kelvin, what we know is Kelvin equals the temperature in Celsius plus 273.15. You know, most textbooks ignore that 0.15 part, but it's okay. So it's given 22 plus 273.15. Then your TK is going to be 295.15 in Kelvin. There is no degree for Kelvin, okay? Keep that in mind. Simple. So it's always just a matter of like, you know, keeping it cool and try to apply the given equations properly, okay? Otherwise, you know. Then let's go for E2. E2 reads like this. The temperature on a winter day is 20 degrees Fahrenheit. Now it's given is TF. In the previous example or problem, it was TC that was given. Now you are asked to determine A. Says doesn't have A, B. It just simply asks you like, what is this temperature in TC? So TC equals 5 over 9 into TF minus 32. Look at the equation. there is a parenthesis here, okay, unlike the previous one. So Tc equals 5/9 into 20 minus 32. So Tc equals 5/9 multiplied by -12. Then your Tc value is going to be like, if you simplify this, then a proper value of about -6.67 degrees Celsius. Okay. So, sometimes you just simply look at the number. Like, for instance, here, the numerical value of Tf is usually larger than the numerical value of Tc. So therefore, if you do a calculation and then, like, if you come up with a Tc value of, let's say, 30 or something larger than 20, then automatically you rule out and then you try to do the calculation all over again. Okay, because common sense tells you that, like, Tf should be larger than Tc. Then the following problem that we're interested in is E6 from the textbook. I'm going to read it. E6 reads like this. How much heat is required to raise the temperature of 90 grams of water from 12 degrees Celsius to 88 degrees Celsius? So I'm going to list out my given parameters. What is the mass? The mass is 90 grams. Temperature initial is 12 degrees Celsius. Temperature final is 88 degrees Celsius. And then the material is water. Since it's water, we know its specific heat. Specific heat of water is 1 calorie per gram per degree Celsius. And now what you're asked to find is how much heat was required to raise that mass of water from that initial temperature to that final temperature. So go ahead and then apply the equation. Q, which is the amount of heat energy required or needed to raise the temperature of a certain mass of water, equals the change in temperature. So Q equals everything, leave it at the way it is, because your CW is, or C of water, is given in calorie per gram per degree Celsius, right? So therefore, you keep your temperatures in degrees Celsius, you keep your mass in gram. Okay, so mass 90 gram, C 1 calorie per gram per degree Celsius. Your temperature change 88 minus 12. Okay, you can eliminate the units if you want. Celsius goes degrees Celsius, gram by gram, because this is a per. This symbol is per. Per means, divide, per. So your Q is going to be 90 times 1 is going to be 90, multiplied by 88 minus 12 is 76 calorie. And if you simplify, or if you plug in this value in your calculator, we're going to get 6,840 calorie. Okay, then let's add one more. E9. E9 states the following. If 900 calorie of heat, that means Q, is given, 900 calorie of heat are added to to 75 grams of water. So the mass of the water is initially at a temperature of 18 degrees Celsius. What is the final temperature of the water? So the way you're going to proceed with this is the following. Start with the original equation for heat or heat energy. Q equals m times C times delta T. So clearly Q is given, M is given, and C is known. Why? Because C of water is standard coefficient that you will be given. Even during exams, it has to be given. I don't think not many professors will expect you to remember those values. Maybe for a few, like for water, maybe for some metallic materials such as aluminum. Maybe otherwise not. Then here we are looking for TF, or the final temperature of the water. So what we need to do is, like, we need to isolate delta T. We need to find delta T, or the change in temperature. Then, you know, that's going to lead us to the answer. So let's divide both sides by MC. Okay, so MC cancels out. Then what we have now is delta T equals Q over MC. Okay, then now your delta T equals Q is what? 900. The mass 75 grams. And C of water is 1 calorie per gram per degree Celsius. So, you know, anything that can be eliminated gram by gram, right? Calorie by calorie. And only thing is left is like degree Celsius. And when you flip it, it's going to up there and it's going to be next to the number. So your delta T, if you simplify this properly, what you're going to get is 12 degrees Celsius. But this is not the final temperature. This is not what you are asked to find, right? But delta T means the following, right? What we know is like delta T equals final temperature minus initial temperature. You know the initial temperature is 18, right? So therefore, if I add T initial on this side, and if I add T initial on this side, that will lead me to the answer, right? This will go away, then you will have delta T plus T initial equals the final temperature. Delta T, what value did you get? 12, right? 12. What value did you get for the initial temperature? It's given in the problem actually. That's 18. So 12 plus 18 is 30 degrees Celsius. Okay, that's the answer. One last question, a question that I like whenever I teach heat and temperature. So this question is like, is there a temperature value when you have like equal value in Kelvin and not in Kelvin, in degree Celsius and in degree Fahrenheit, right? Like the question is, I'm trying to frame it like, is there a numerical value? Of course, it's temperature value, you know? Is there a numerical temperature value that is the same? Or equal, rather. That is equal in both degree Fahrenheit and degree Celsius. So it's consider it like this. There is 0 degrees Celsius, right, is equal to 32 degree Fahrenheit, right? That's what we know. What I'm saying is, like, is there any way that, like, a certain number, let's call that number x degree Celsius, is the same as x degree Fahrenheit? Okay, so to answer that question, you can go ahead and then apply one of the equations. I mean, you just go ahead and then apply the unit conversion equation, like from Kelvin to Celsius, right? And then substitute x for both. It's like this. So for instance, so we can start with the equation, one of the equations. Like, for instance, you can start with the one that has like TF or TC. So for instance, TF is what? 9/5 TC plus 32, right? So now how we are approaching this is, like, you have x for TF, then you have x for TC, then plus 32. Then collect like terms. That means you take this to the other side of the equation, then it will be minus, right? 9/5x equals 32. So you can have a common denominator between 5 and 1. That will be 5. 5 divided by 1 is 5 times x, 5x. 5 divided by 5 one time, 1 times 9 is 9. Right? So 5x minus 9x is, of course, it is 4x, negative 4x. Divided by 5 equals 30. Now, if you might multiply this side by 5 and divided it by negative 4, I have to do the same thing on this side. Multiply that by 5 and divided it by negative 4. Why do I do that? Because I just want to isolate x. I want to have x by itself. So if I do that, everything else will be deleted and I'll only have like x by itself. Then 32 times 5 is 160 negative divided by 4. So x will be negative 4, negative 4. So what does this mean? This means at negative 40 degrees Celsius, you have negative 40 degree Fahrenheit. So those two values are the same. This is the only temperature value that you are going to get. Both of them have the same numerical value, and of course both of them mean the same coldness or the same hotness. You can put it that way. Okay, so at negative 40 degrees Celsius, you have also negative 40 degree Fahrenheit. Okay, so with this, well, we wrap up chapter 10. Take your time when you solve those problems. Of course, it's like for the video, this is a little faster, but probably you may need to spend about like from 2.5 hours to 3 hours of your time trying to understand the video, try to solve the problems and all that. Okay, so until the next time and next material, then see you.